Hello, my dear students. So, first of all, welcome to most expected MCQ series. So, that is concept through this question. And here, I would like to know your feedback with respect to discussion itself. So, here, I would like to know about that whether you are feeling comfortable with this English session only, or you want this into mix of Hindi and English, or if you want this completely into Hindi, then I should know about that. So, you give your feedback through the comments so that I'll be knowing about that, because some of them were asking that please do the session only in the English. So we belong to South India. So I need to take care about that. All those, even though some of the students are from North India, some of them are from South India also. So I need to take care about everyone. So if everyone is comfortable with this English itself, then I'll continue this session in the English itself. Otherwise, I have to make the mix of Hindi and English or both of that. So now I'm going for this day 2. So here for this day 2, the first question here it is given as a question number 11 is diffusion current in a semiconductor is caused by option A electric field, option B concentration gradient, option D magnetic field, option D temperature gradient. So here if you see that diffusion current, how it is given, that is given for this J P diffusion is given as a minus Q into dP by dx. And similarly, for the electron, this is given Jn diffusion is equal to, in this Q, let's say this is equation number 1. So this is the expression for the positive mobile charge carriers as a whole. If we will talk about that electron, so electron is having the negative charge, so we need to replace in this Q by minus Q here. Then this will transform this diffusion current equation, diffusion current density equation for the N type of the semiconductor. So this will become now Q will be replaced by this minus Q. So minus it will become here as a plus. So this will be simply Q into dP will change to dN, and this dP by dx will change to dN by dx. So here this Q is electronic charge, dP and dN is called diffusion coefficient or diffusion constant, and their unit will be given. So this dP or dN, their unit is given normally in EDC part, it is given centimeter square per second. Sometimes they ask about that unit also. And this dP by dx is called, dP by dx is called as a concentration gradient for holes. dN by dx is called concentration gradient for electron. So here, what they are asked, diffusion current, they are asked here as a diffusion current in a semiconductor is caused by. So as per that, you can see it here, concentration gradient is the most appropriate answer for this question. So by this way, option B is the right answer for this question. Now we'll move to the next. So next question is given. The mobility of electrons in silicon is generally option A less than hole mobility, option B equal to hole mobility, option C greater than hole mobility, option D 0. So here they had asked about that mobility of electrons. Mobility of electrons is generally denoted by mu suffix n, and here as we know that mass of the electron is much lesser compared to mass of the holes. So due to that, those who are having lighter mass, they can run faster. So the mobility of the electron is much faster compared to the mobility of the holes here. The reason behind that, masses of this electron, or I can say that effective mass of electron is lighter compared to the effective mass of holes, and mobility is inversely proportional to the effective mass. So due to that reason here, the mobility of the electron is much higher compared to the mobility of the hole. So here what they ask, mobility of electron is greater than hole mobility. So that option C is the right answer for this question. You have to write each and every point, whatever I am saying here. These all the points can be transformed as the questions also in some of the exam and even many of the competitive exam also. So next is Hall effect can be used to determine carrier type, carrier concentration, magnetic field, all of the above. So here if you see it here, then if you have studied about that Hall effect, it is not there for the GATE syllabus, but it is still there for that ESC syllabus and some other competitive exam. So if you go through that, then you will be finding that Hall effect is used to find out the carrier type, carrier concentration, magnetic field, all of the above, so that the right answer will be all of the above. Option D is the right answer for this question. Now we'll see for the next. So next is, at thermal equilibrium, the Fermi level is different throughout the semiconductor. Option B, constant throughout the semiconductor. Option C, equal to the conduction band energy. Option D, equal to the valence band energy. Dear friends, this is very important concept what I am going to discuss you now. At thermal equilibrium, the Fermi level is different throughout the semiconductor, constant throughout the semiconductor. Yes, so this option B is the right answer. So whatever we had seen earlier, for example, this is our P type of the semiconductor. Here, as per their energy band diagram, this is their VB, this is their CB, and this side it is having their Fermi energy level, and this side, if you see it here, this is for the P type of the semiconductor. This is P type, sorry, this is the N type of the semiconductor. So here, for this N type of the semiconductor, how the things will change? The things will change in this way. This side it is having, this is valence band, this is their conduction band, this is their EV, this is their EC, and their Fermi energy level is lying somehow at this point EF. So when we talk about that independent N type, P type, if there is no conduction of the current through the semiconductor or through the device, at thermal equilibrium, this Fermi energy level will be flat. It will be constant throughout this semiconductor, even throughout this semiconductor. Whenever you are going to join these two, then EV, EC position can change. So this is their EV, this is their EC, but under the condition of no current passing through that, then EF must be flat, so that will be joining together, and that is the reason that bending of the EC, EV is taking place in the case of PN junction diode. So here just we should know about that. At thermal equilibrium or under no conduction or no current is flowing through the material, through the device, then in that situation Fermi energy level will be constant throughout the device, throughout the material. So due to that reason, option B is the right answer for this question. You must have to note down these points also. So now we'll see next. So next is the mass action law for a semiconductor is. So with respect to semiconductor, this is one of the most important law whatever we are going to study under this EDC part. So mass action law is giving the idea about that in an extrinsic semiconductor at a given temperature, this law or this formula is used to find out the concentration of the minority charge carrier. So here, how it is given concentration of the majority and minority, it is giving here NP is equal to NI square. So let's say for N type of extrinsic semiconductor, what is the minority charge carrier? That will be whole. So that can be obtained here. P is equal to Ni square divided by a small n, or simply we can say Ni square divided by Nd. So in N type of the semiconductor, whole is called the minority charge carrier. So to obtain that minority charge carrier concentration, we are using this mass action law. Similarly, for P type of the semiconductor, electron is the minority charge carrier. So the concentration of electron we can obtain N is equal to Ni square divided by P, or simply Ni square divided by Na. So this can be, this formula you can note down to solve some problems based on this mass section law. Whenever they're asking about that minority charge carrier concentration, then in that case we can use this. So based on this, what is the right formula here? That option B is the right formula here, which is describing about that mass section law for a semiconductor. So mass section law is applicable only in the case of semiconductor. The reason behind that, in the case of metal, there is no holes, there is only one type of charge carrier as electron. So mass section law is not applicable in the case of metal. It is applicable in the case of semiconductor, where we have the concept of majority charge carrier and minority charge carrier. So this concept is used, this formula is used to find out that concentration of the minority charge carrier in an extrinsic semiconductor. So by this way, option B is the right answer for this question. Now we'll move to the next. So next is, in a semiconductor, the Fermi energy level depends upon option A, doping, option B, temperature, option C, both A and B, option D, none of these. So my dear friends, I would like to tell you about that this Fermi energy level is depending upon doping as well as temperature. So when I will deal about that concept, there I will give you the derivation of that formula also. Then from there you can find out very easily that how Fermi energy level can be changed by changing the doping of the semiconductor or by changing the temperature. So based on that, here this option C is the right answer for this question. So option C is the right answer for this question. Now we'll move to the next. Next is, the units of the mobility are option A, centimeter square per volt per second, option B, centimeter square per second, option C, centimeter square per volt, option D, centimeter square per second. So here, how this mobility is defined here? We know that this Vd is called the drift velocity. Vd is called the drift velocity, and this is given here as a mu into E. So from here, this mobility is defined here as a drift velocity per unit electric field. So the unit for this drift velocity, whatever is the velocity, it is having the unit of centimeter per second or meter per second. So in this case, I am taking here as a centimeter per second, and this electric field intensity is having that unit of volt per centimeter. So if you see it here, then what it is giving their unit, centimeter per second divided by volt per centimeter. So simply centimeter will go to the upside, so that will become here centimeter square per volt per second. So the unit for this mobility is simply centimeter square per volt per second. Option A is the most appropriate and right answer for this question, and you must have to remember this because several times there are these units for this mobility in so many competitive exams. So now we'll move to the next. The probability that an electron in a metal occupies the Fermi level at any temperature 0 degree Kelvin. Option A is 0. Option B, so here it should be greater than 0 degree Kelvin. It is the probability that an electron in a metal occupies the Fermi level at any temperature greater than 0 degree Kelvin. It should be here corrected as greater than 0 degree Kelvin, not at 0 degree Kelvin. I'll explain why it is. So here, as per the Fermi-Dirac function, this function is given Fne is equal to 1 by 1 plus exponential E minus Ef divided by Kt. So what they had asked? The probability, here in the question what they had asked? The probability that an electron in a metal occupies the Fermi level. Occupy the Fermi level means this E should be equal to Ef. If E is equal to Ef, it means this difference will become 0. And if the temperature is also 0, then this will become a 0 by 0 form, which is not the proper defined here. So due to that reason, this we should not take exactly 0 degree Kelvin. It should be greater than 0 degree Kelvin only. It is defined here. So if you substitute this, EF is what? Fermi energy level. K is Boltzmann constant. T is temperature in degree Kelvin. E is any arbitrary energy level which is occupied by the electron. So that probability is given here as a Fne. So if you substitute in this equation 1 as a E is equal to EF, then what you will get it here? This Fne is equal to 1 by 1 plus exponential. If you substitute here, this E is equal to EF, it means it will become a 0 by kT, so that will become simply exponential 0 here. So we can say it here 1 by 1 plus e to the power 0, it means 1 by 1 plus 1, it means 1 by 2, so that is simply 0.5. So here the answer for this question will be option C, 0.5 is the right answer for this question. And you must have to note this Fermi-Dirac function formula to find out or to solve such kind of questions. So now we'll move to the next. So next is the units of Q by kT are. Option A, V means volt. Option B, per volt. Option C, joule. Option D, joule per Kelvin, or simply we can say joule per degree Kelvin. So here, if you recall that, or if you have studied Einstein relationship in the ADC part, then what it is giving? It is giving that diffusion coefficient or diffusion constant divided by mobility is equal to kT by Q. So kT by Q is called simply thermal equivalent voltage. Thermal equivalent voltage. So as per the Einstein relationship, it is given D by mu is equal to kT by Q. So this kT by Q is nothing but it is voltage. So here this Vt is given as a kT by Q. Now their unit is volt. If we reverse this, Q by kT, then what will be their unit? It means it will be per volt. It will be per volt. So V raised to minus 1, or simply we can say per volt. So option B is the right answer for this question. Here itself I would like to give you their unit already we had seen. Unit of the mobility already we had seen. Now here we can define the mobility of this diffusion coefficient. So for the electron it is given as a dn, for the hole it is denoted as d suffix p. So here we can say that d is equal to mu into Vt. Mu into Vt. So this d is in general we can use it here. So for the electron it will be dn, for the hole it will be dp. So I am writing it in general. So for the mobility we had seen the unit is centimeter square per volt per second. And here the unit for this thermal equivalent voltage. So voltage is having the unit of V. Voltage. So now here, if you see in this one, this V and V gets cancelled. So this is giving the unit of centimeter square per second. So here just I am going to summarize that mobility is having the unit of centimeter square per volt per second, and the unit of this D is simply here what we can say, D is what? Diffusion coefficient or diffusion constant. So this is having the unit of centimeter square per second, and then again what we had seen, kT by Q is having the unit of volt, and here Q by kT is having the unit of per volt. So this data you can remember what the units are. I have derived here. You can make a list of all these, because this will be very useful for the competitive exam point of view, and by that way you are learning all those things. So you must have to keep these in your notes. So by this way the answer for this one is option B is the right answer for this question. Now moving for the next question. A long specimen of p-type semiconductor material, option A, is positively charged. Option B is electrically neutral. option C, has an electric field directed along its length. Option D, acts as a dipole. I would like to say you here, any type of semiconductor, even for the intrinsic semiconductor, electrically it is neutral. For P type of semiconductor, electrically it is neutral. For N type of the semiconductor, electrically it is neutral. And these kind of questions, most of the time, students are doing the mistake. What the mistake? If it is mentioned P type of the semiconductor, they understand that this will be positively charged. It is completely wrong. P type semiconductor is giving here, just look at it. For P type semiconductor, majority charge carrier is holes. They did not ask about that holes. So here, this P is much greater than N. And electron is minority charge carrier here. Similarly, for N type of semiconductor, electron is majority charge carrier, and this is much higher than holes. It doesn't mean that it is negatively charged, it is positively charged. How? So here itself, in P type of the semiconductor, we have the majority charge carrier, minority charge carrier, as well as we have it here negative acceptor ions also. So apart from this, it is having negative acceptor ions also. Similarly, for the N type of semiconductor, it is having positively donor ions, positively charged donor ion. And as per the electrical neutrality, their general equation is written here as a N plus Nd. This N plus Na is equal to P plus Nd. So what do you mean by this? This N is called negative mobile charge carrier as electron, and this Na is called acceptor negative ions. So both the type of charges, both the type of similar charges can be added together. Similarly, to the right hand side, P means holes. Holes is having positive charge, and Nd is called what? Doping atoms. So their concentration is same as like positive donor ions here. So this can be added together. So let's say for N type of semiconductor, what will happen? This Na. For N type semiconductor, their Na is equal to 0. There is no acceptor atoms added into this. What the atoms it is added? Pentavalent impurities. So which is forming a positive donor ions. So based on that, for the N type semiconductor, this Na will become 0. It means this equation can be rewritten here as a small n is equal to P plus Nd. What do you mean by this? N is called here the doping concentration. This N is called here concentration of electron as a majority charge carrier. This P is called what? Concentration of minority charge carrier as a holes, and this Nd is called doped atom. So here, if it is complete ionized, it means this will be having these many number of ions it is forming. So now if you see that the concentration of negative charge electron is equal to the concentration of positive donor ions plus the minority charge carrier as a whole, which is also having positive charge. So this, if you see that number of negative charge, number of positive charge is same for N type of semiconductor, so electrically it is neutral. In the similar way, for P type of the semiconductor also, if you see it here, that the number of positive charge mobile charge carrier as a whole is equal to the number of negative acceptor ions plus the number of electron concentration, both is matching to each other. So due to that reason, electrically it is neutral. So that option B is the right answer for this question. By this way, day 2, 10 questions is completed. Now it's time for you, for your scorecard. How much you have scored, you have to give your answer genuinely by commenting at our channel so that I'll be knowing that how you're doing the work and how much it is on the track. So now based on that, this is the scorecard. So you have to do that self-evaluation and check it about that and send me your marks, whatever you obtain out of these 10 questions through that message, so that I'll be knowing about that. Thank you for watching this video. Then we will meet again in the next video with the next set of questions. Thank you.